Welcome to an elementary synthetic geometry-based introduction to inversion of the real plane with respect to a circle course, episode 12, seminar 3, in which we will solve our next problem, 13, in which we're asked to construct all circles that are tangent to three given fixed coplanar circles that intersect at a point to which we will refer as P for the sake of definitiveness. And if you understand what does it mean when two circles intersect, then you can skip forward to the next segment. If you do not understand what does it mean when two circles intersect, then the meaning of the word intersect in this case should not be underestimated because it is a key for this problem. And we should understand that if and when two circles intersect, whether these two circles belong to one and the same plane or to two distinct planes, then they do so over exactly and only two genuinely distinct points. That means that, for example, the yellow circle shown on the left and the light blue circle shown on the right intersect over two and only two genuinely distinct points. This point right here, to which we will refer as P, and this point right here, which I did not designate in order to avoid the clutter. The light blue circle shown on the right and the electric green circle shown on the bottom intersect over two and only two genuinely distinct points. This red point right here, which we named as P, and this point right here, which I did not show in order to avoid the clutter. And lastly, the electric green circle shown on the bottom and the yellow circle shown on the left intersect or have exactly and only two genuinely distinct points. This point that we name P and this point right here, which I did not show in order to avoid the clutter. And as such, I think one of the most descriptive or intuitive languages or terms in which the intersection of two circles can be used is the language of common points. In other words, if two circles intersect, then they have precisely two genuinely distinct points in common. From the set theoretic standpoint, if we describe the objects that were given in this case as sets of points, then the set theoretic intersection of, let's say, yellow points and light blue points will be precisely 2 points, this one and so on. The intersection of the light blue points and the green points will be these 2 points here, and the intersection of the green points and the yellow points will be this point and this point right here. In other words, the intersections of all 3 circles in this case will be represented by 3 distinct sets. And in each such set, there will be one point that will be private to these 2 specific circles, and there will be one point that belongs to all 3 sets. In other words, the set theoretic intersection of the intersection sets will be precisely one point, and that is the point which we named as P, and that is the point where the circles intersect. And for those of our viewers who feel slightly more comfortable with the algebraic side of things, let us say that in this specific and pronounced two-space situation, to each point of interest, we attach a coordinate, which is an ordered pair of real numbers. Then when two circles intersect, as they do in this problem, then at least one component in the coordinates of the common points to 2 circles must be different. For example, let us say for demonstration purposes that our yellow and light blue circles intersect over vertical points. What does that mean? It means that the x component of both of these intersection points will be one and the same, but the y components of these points will be different. These components will be described by distinct real numbers, y. And the other way around. Let us pretend for demonstration purposes that the electric green circle and the yellow circle intersect over the horizontal 2 points. What does that mean? It means that the y component of the coordinates of both of these intersection points will be the same, but the x components of both of these points will be different. In this case, also the sets of intersections of our circles will be represented by three sets. Each of these sets will contain two distinct pairs of coordinates, and in these coordinates, if one of the components is the same, the other component must necessarily be different. Now that we understand the mechanics of the mutual juxtaposition of the given circles, let us contemplate what type of solutions are we to expect in this problem to begin with. By the looks of it, we should be able to have, in this case, one unique circle that will touch all three given circles internally. In other words, one circle will contain all three circles. And why is this circle unique? This circle will be unique for the following two reasons. In this case, there will be three distinct points of tangency. And this point of tangency, each one of these points is unique. Why is that? Because each such point is the point that is the limiting position of a second straight line. In other words, if two curves, whether in two space or three space, intersect, they do so precisely over one or a single point. Not 0 points, not 2 points, not 3 points, but precisely one. As such, there will be three distinct points over which we will construct, or should be able to construct, a circle, one solution circle that will touch all three given circles internally. And then also, by the looks of it, we should have another three distinct or unique circles, which will have the following property. Each one of these three circles will touch one of the given circles internally, while touching the remaining two externally. For example, we contemplate that there should exist a circle that touches the yellow circle internally, while touching the light blue and the electric green circle externally, roughly like so. And the same idea applies to all the other circles. We should have the third solution circle that touches, for example, the light blue circle internally, while touching the yellow and the green circle externally. And lastly, we should have the fourth solution circle that touches the electric green circle internally, while touching the light blue and the yellow circle externally. Now, how do we find these solution circles? We find these four solution circles by following the heuristic template, or a problem-solving approach that we described in episode 10, seminar 1, which amounts to a search for a fruitful center of inversion, power of inversion, radius of inversion, and a composition of inversions such that the inversion of the local material in the chosen parameters produces a problem that is much more tractable, or a problem that is easier to solve. Perhaps even this inversion of the local material generates a previously solved problem. And if we're able to do that, then we can exactly exercise the tactical advantage of inversive geometry. And then we are to convert the solution of the problem in terms of the inverted objects into the solution of the original problem in terms of the original objects. As such, in this particular problem, what is a fruitful center of inversion, radius of inversion, power of inversion, and composition of inversions? Well, at this point, it should be evident that the very point P over which all three circles intersect, this is our point P. I'll designate it now explicitly. This point P should be chosen as the center of inversion on the first attempt. Remember that in mathematics, there are no guarantees. When we solve an interesting problem, we're pretty much destined to make several assumptions or several tries that will fail, try, fail, and then eventually and hopefully we succeed. So in this case, it is not guaranteed that on the very first try we will succeed, but it turns out that this is exactly the situation in this problem. If we choose the point P over which three given fixed coplanar circles intersect, then what will happen? Well, we recall right away the series of theorems in which we proved that for the most part, any straight line that does not pass through the center of inversion is taken by the corresponding inversion of the real plane with respect to a certain circle into a circle that passes precisely through the center of inversion, and conversely, any circle that does pass through the center of inversion, which is the case for all of our three circles, that circle, regardless of its mutual juxtaposition with respect to the circle of inversion, will be taken into what? Into a straight line. And we know that straight lines in general are somewhat easier to deal with than circles. So once we nail the point which will play the role of the center of inversion, we think, what should be the radius of inversion? Well, here it is evident that for the most straightforward solution of this problem, we should take for the radius of inversion such a strictly positive real number that the circle of inversion will intersect. Again, it comes back to the discussion of intersection between two circles. So our circle of inversion should genuinely intersect all three given circles. Such sample circle of inversion, designated with the lowercase c, is shown over here in white. As we can see, I picked such a radius of inversion which guarantees that all three circles are genuinely intersected by the corresponding circle of inversion. For example, our circle of inversion C, lowercase c, intersects the yellow given circle at this point and at this point. The circle of inversion C intersects the light blue circle here at this point and at this point. And the circle of inversion C intersects the electric green circle at this point right here and at this point right here. What does this maneuver buy us? Well, for the third step, now that we picked the center of inversion and the radius of inversion, we need to think about the power of inversion. Like I said before, usually the positive power of inversion will be more than enough, even though at some point in the episode, which will be titled An Arbelus Encounter, we will meet a problem where the inversion of the parent plane with respect to a circle with negative power makes wonders. Here it is enough for us to deal with positive power of inversion, and once we made all our decisions and locked in our parameters of inversion, the intersection point P as the center of inversion, a radius of inversion such that the corresponding circle of inversion intersects all three circles, and in that sense the actual magnitude of the length of the radius of inversion is irrelevant modulo the requirement that this radius should ensure that the circle of inversion intersects all three given circles. The power of inversion should be positive. One inversion of the parent plane with respect to the chosen parameters is enough. Why is that? Well, we know that under the chosen parameters, all of our given fixed coplanar circles that intersect at a given point will be taken into what? They will be taken into straight lines that have the following two interesting properties. First of all, we can construct these straight lines using Euclidean tools alone right away. This is the byproduct of our theorems that we proved in problems that we solved, number one. Number two, recall that under any inversion of the parent plane with respect to a circle, so long that the sample point is distinct from the center of inversion, which in our case all interesting such points are distinct from the point from the center of inversion, the other points where the circles intersect, the image of such a point is always unique. That means in general that if our circles intersect, then their images will also what? They will also intersect. For example, let's take a look at the point where the light blue and the yellow circles intersect for the second time, excluding the common point where all three circles intersect. Remember, in the previous segment we had the discussion. A set contains two objects. One object is private to that pair of circles. The other one is common to all three circles. So this point over here is common to two objects at once. It belongs to the light blue circle and it belongs to the yellow circle here. But the image of that point under the chosen inversion, that point is distinct from the center of inversion, will be a point that is what? That is unique. It will be only one. But that point will also belong to two objects at once, the images of our circles under the chosen inversion. And that means that in this case, the three straight lines that will be the images of the three given circles will also intersect. And the three straight lines in a plane intersect, they form what? They form a triangle. For example, let us take a look at the material that we obtain once we invert the parent plane with respect to a circle C, white circle shown over here that has the point P as the center, and a radius such that that circle intersects all three given circles. The circle Q1 that I labeled over here, Q1, the light blue circle, will be taken into a straight line L1. And we know that with Euclidean tools alone, we right away, without much thinking, can construct the image of that circle. We will mark it that the power here is positive. Plus r squared, the power is positive. When the power of inversion is positive, then the construction is especially pleasant. All we have to do is identify the points that are common to the circle of inversion and the pre-image circle, the light blue circle Q1, and snap a straight line, which I called L1, that passes through these points. Game over. In this case, we do not even need the Euclidean compass, the Euclidean straight edge, of which this here thing is an incredible simulation of. This is all we need. We snap a straight line through these two common points, this point, and thus we obtain the straight line L1. Moving on to the circle, the yellow circle Q2, this circle under the chosen parameters of inversion will be taken into a straight line, which we can construct how? Well, this is one point where the circle of inversion and the pre-image yellow circle intersect, and this is the other point where the circle of inversion and the pre-image yellow circle intersect. In order to construct the image of the yellow circle Q2 under the chosen inversion, all we have to do is take our magnificent straight edge and snap a straight line through these two common points, and the game is over. We thus obtain the straight line L2. Lastly, the image of the electric green circle named Q3 will be constructed under the chosen inversion. Which way? We identify this here point as the point that is common to the center of inversion and the pre-image green circle. This is the second point that is common to the circle of inversion and the pre-image green circle, and we snap a straight line through these 2 points, and voila, game over. Look at how beautiful, elegant, and crisp our solution is unfolding so far. This is the straight line L3. Again, we talked about the importance of the word intersect in the statement of this problem. There are no tangency points, so our configuration is always valid. It will never happen that we will have one straight line perpendicular and another perpendicular. In other words, our 3 lines will always genuinely intersect. They will always genuinely form a triangle shown over here. I do not want to designate to pollute this drawing with more symbols than I have to. You understand what is going on. This seminar is based on the corresponding chapter. The link to that chapter as a free PDF file is in the comment section. You can click, open, take a look. I have a nice diagram there. But the important thing to understand is that once we invert the local material that represents a difficult to solve problem, what do we obtain? Well, we obtain precisely the tactical advantage that we are after with this maneuver. Why is that? Well, we know that every non-degenerate planar Euclidean triangle, such as our triangle formed by the intersecting images of the given circles, possesses four unique circles that touch the corresponding sides or the extensions of these sides. The first such unique circle will be the in circle. That in circle is shown in blue right here. This is the circle. And we know how to construct it. As a refresher, as a crash course on this construction, it is shown on the lower right side of your screen. If this is our sample triangle, it is enough to construct just two angular bisector of the interior angles of this triangle. For example, this one and this one. Two such bisectors will intersect at a unique endpoint that is located, let's say, here, and then from that point we drop a perpendicular onto any side of this triangle. It doesn't matter, I show here a sample side. That line segment will lock in the unique in radius, and we snap a circle, and this is how we construct the in circle of such triangle. The point is, that problem can be solved with Euclidean tools alone, just like that. This is a not only a previously solved problem, but this is also a trivial problem. And that is precisely, one more time, I want to emphasize this fact that the whole reason we come up with these heuristic templates, problem-solving approaches, and all this magic is to gain a tactical advantage. And this is exactly where we gain a tactical advantage. Drawing a circle that touches all three sides of the given triangles internally is a trivial problem and a previously solved problem. This is where we gain the tactical advantage. What are the other three unique and distinct circles? Well, these are the so-called X circles, and they are constructed in a similar way. For example, I showed the construction of one X circle on your right side over here. What do? Well, we take the corresponding two angular bisectors of the external angles, this angle right here and this angle right here. These two angular bisectors will intersect at this point right here, and from this point we can drop a perpendicular to the extension of this side or of this side or of that side. It doesn't matter. This point is equidistant from all of these three sides, and then we snap an X circle shown right here. Again, by the same reasoning that I mentioned before, that all our solution circles are unique because three distinct points of tangency are generated. Any three distinct points define a unique Euclidean plane, a unique Euclidean triangle, and a unique circle. And if these circles are chosen at the right place, these circles will be unique. In other words, the unique X circles means the following. On that side, there will be only one circle that touches the extensions of this side and this side externally. There will be no other such circle over here on that side. Likewise, there will be one circle, X circle over here, and one X circle over here. 1, 2, 3, 4. Game over. We understand how these things work and bringing home the tactical advantage. Now, remember, we go back to our heuristic template and recall that, what do we do now? Now we convert the solution of the problem in terms of the inverted objects into a solution of the original difficult to solve problem. How do we do this conversion? Well, in this case, the conversion is more than straightforward. We carry out the inversion of the parent plane with respect to the same center, radius, and power. In other words, we reflect our constructed by us in circle, shown over here in blue, in the white circle C with positive power once. And once we do that, what do we do? Well, here we'll have to go through our course, pull out the number of the theorem, in which we prove that any circle that does not pass through the center of inversion is taken by the corresponding inversion into a genuine circle. Here, at the risk of overloading this discussion with too many technical details, through the series of theorems, through all 44 theorems that we proved in this course, we actually showed that topologically, a circle and a straight line are equivalent. And as such, we can merge the two notions into one circline, for example. But forgetting about this for a moment, our unique in circle for the triangle that is formed by the images of the given circles under the chosen inversion will be taken into a circle shown over here. This is the blue circle shown over here that will touch all three given circles that intersect at the given point. Internally, look at this. The point of tangency will be right here. The second point of tangency will be over here. And the third point of tangency will be over here. And from our Euclidean tools only exercises, remember, let's say we identify the point of tangency of the in circle with our triangle as this one. Well, we know that that point, the image of that point must be collinear with the center of inversion. And once you do everything nicely and professionally with the tools, you will see, that looks reasonable. The point of tangency should be here. With this one, the point of tangency should be here, here, and somewhere here. And the third point of tangency should be where it should run somehow from here to here and to somewhere here. So that looks realistic. I wasn't too bad with my by eye pretty much drawing. And when we carry out all these constructions with a graphing software, nicely, neatly following all the rules, then such a solution will look as follows. And if we patiently throw all the other remaining x circles in other words, we construct one x circle on this side by constructing the angular bisector here and the angular bisector here. We also bisect this angle and this angle, obtain the point, drop a perpendicular, draw the circle, and we do the same thing for this side. Angular bisector, point, perpendicular, circle, and we construct 1, 2, 3 x circles. And once we reflect these circles in the chosen circle of inversion with positive power ones, then done with the graphing software, let's say professionally, that solution will look as follows. And now that we understand the motivation behind the solution steps that we developed in this analysis, and we understand exactly why, where, and how we gain a tactical or a competitive advantage while solving this problem, we can put down an algorithm that solves this problem using the Euclidean tools alone with absolute certainty and correctly. Do not worry about missing any of the algorithmic steps that we're about to discuss, because this episode is based on the chapter number 10 of my free book, Inversive Geometry for All. The link to that chapter as a free PDF file is in the comment section to this episode, but instead try to concentrate on the big picture and understand from the biggest scope of things perspective, how did we solve this problem? Intuitively speaking, and in a lightning round, take the difficult to solve problem, invert it into the problem that is easier to solve that easier to solve problem, generate a solution of the easier problem, and then reverse transform. Untransform, let's say, the solution of the easier to solve problem or the solution of the problem in terms of the inverted objects back into the solution of the original difficult to solve problem. And once you understand that big picture, you will be able to reproduce and fill in all the relevant details on demand if need be, but the algorithm for the solution of this problem with Euclidean tools alone, with absolute certainty and correctly, is the following. First, invert all the given objects in the circle such that it has the point P where all three circles intersect as its center, and the radius such that the corresponding circle of inversion genuinely intersects all three given fixed coplanar circles Q1, 2, 3 that intersect at a given point with positive power once is enough, as explained, into the corresponding objects. Again, I do not want to pollute the description with too many symbols, but here you will write that the string of symbols that you saw on the right side of your screen before, the circle Q1 into the straight line L1, Q2 into L2, Q3 into L3, three circles, three straight lines that intersect. And as a second step of our algorithm, you will construct one unique inner circle with the resultant non-degenerate Euclidean triangle that is formed by the three intersecting straight lines and three X circles, as I explained, angular bisectors, intersection point, perpendicular, and so on. Once you construct these four objects, as the step number 3 of our algorithm, step number 3, you invert the parent plane, which means the above four circles that we constructed in the previous step, in the same circle, with the same center, with the same radius, with the same power, also once into the sought after solution circles that touch all three given circles that intersect at a given point. Again, on my board, I do not want to mess things up too much. I want to keep the clarity of just one solution present on the board so that you understand how all the other solutions are developed and are obtained. Again, I have a nice diagram for each problem that we solve in this course in the corresponding PDF file. Click, take a look, I suggest that you carry out all these constructions yourself to develop a better feel how this theory and practice work together when combined, and that's how you drive the understanding of the underlying mathematics into your bone marrow. And before we conclude the solution of the problem 13, as a fun and informal quiz, in a few seconds you will see an animated demonstration that I put together for you using the free software called GeoGebra. And as you watch that demonstration, try to answer the following question: why am I showing it to you, and what is going on in that demonstration? In the animated demonstration that you just saw, I wiggled the position of the point that controlled the radius of the circle of inversion C by changing its position back and forth a couple of times, and this is what you were expected to observe. When the radius of the circle of inversion changed within the boundaries of the requirement that this circle intersects the given three coplanar fixed circles, all of which intersect at a given point P, then the size of the corresponding triangle that was formed by the three lines that were the images of the given circles with respect to that circle changed. I made it smaller, I made it a little bit bigger, and consequently the sizes and the positions of the corresponding in circle and the four X circles also danced in some elaborate way in unison with that change. However, the important thing that you were expected to observe, during this demonstration is that the solution circles, all four solution circles, did not move a muscle again. They stayed where they were, regardless of how the size of the corresponding triangle and the size and the position of the in circle and the 3x circle changed. And at some point in this demonstration, I took the radius of inversion of this particular setting to a point where the circle of inversion did not genuinely intersect the given circles. In other words, I violated this requirement, and you saw that one by one the solution circles popped out of the existence altogether. But when I brought the radius of inversion back in such a way that it honored the intersection of the three given circles requirement, then the solution circles popped into existence one into the other. This is what was happening. This is what you were expected to see. And the reason why I put this animated demonstration for you is to imprint on your minds one more time the fact that modulo the requirement that the radius of inversion is such that the corresponding circle genuinely intersects all three given circles. If we forget about this requirement for a moment, then within the boundaries of honoring that requirement, the actual radius or the actual length of the radius of inversion was irrelevant. This is going back to the remark that I did in the first or the second lecture when I said that the radius of inversion many times is irrelevant itself, and as such can be set to positive unity. Now, this is it for the problem number 13. In the next seminar, this will be episode 13, seminar 4. I recommend that you review all the previously studied theoretical material, review all the problems that we solved so far, because for that seminar, you should really bring your best game, because in that seminar we will be solving a much more challenging problem that is known as the three-circle Apollonius problem, in which we will be looking for ways to construct all circles also tangent to three given fixed coplanar circles, but the circles will be in their general position. We will not be assuming that the circles intersect at a given point. In some sense, the solution of the problem that we developed in this seminar will be a subset, if you will, of the solution that we will develop in the next seminar. But for the next problem, try to think on your own what will happen if we unbuckle all these three circles, and such three circles still belong to one and the same plane. They will be obviously coplanar, but they will be in the general position. Let's say they do not even have any points in common. Each one is located outside of the other one. How would you find a way to construct all circles that are tangent to three circles that are positioned like so?